In this video, I will show you the 3D slot construction and nesting template, which is a Grasshopper definition that shows you how you can do 3D slot construction from sheet material. So what this means is we have a construction in which we have flat pieces of sheet material. That could be wood, could be cardboard, could be any material, metal, acrylic, plastics, whatever you want to use in your project. And we then cut slots into this material in such a way that we can assemble three-dimensional structures from it. So we have very simple material that can be cut very easily on a two-dimensional process, and then we can assemble quite complex 3D geometry from it. And depending on the material you want to use, you might want to use different parameters and different kinds of slots, but Grasshopper gives us a very simple way of creating simple slots that I want to show you in this tutorial. And of course, you can go on and explore more sophisticated ways of creating these slots. So in Grasshopper, the way the process works is we use the region Slits component. And you can find this component in the Intersect tab in the top. And all the way on the right, we have this region Slits component. You can also use the box slits component. It's very similar to the region slit component, but I like to use the region slit component because it gives me a bit more freedom, and it's just a bit simpler to use. But basically, both of these components do very similar things. So we have two pieces of geometry, and these should be flat surfaces. So these need to be absolutely flat. They cannot be curved in this direction. Of course, they can have any shape you like, but they need to be absolutely flat. So all points on this surface need to be in one plane. Otherwise, the process won't work. And of course, these pieces of geometry should intersect each other. Otherwise, we will not have a slot that is created. We then use this merge component to create a list from these multiple pieces of geometry. Of course, you can add as many as you like. I could just add more into this merge component here. We should make sure that these are flattened. So the intersections between all of these surfaces are calculated. And then we can basically create the region slit. This, of course, needs a material thickness parameter. And this is just the width input in the region slits component that can be set here with the material width slider in the template. Depending on your material, you might want to add a bit more or less to your material, because when it is cut, of course, sometimes your cutter, for example, a laser cutter, might cut away a bit of the material. So if you use the actual material thickness, you will basically end up with slots that are too wide. So you might want to just reduce this slightly depending on your material. But most of the time you will have to test this and figure this out to make sure you have slots that then fit together nicely without a lot of gaps between them. And yeah, this is basically how we can then create these slots. And if you want to use Rhino, and if you want to create this geometry by hand, or if you already have some kind of geometry that you want to use, you can simply go ahead and use this very simple group up here to create your project. But I've also created an example that is a bit more interesting, that has a lot more faces, a lot more intersections, and that also uses the nesting components from OpenNest. That would then allow you to not only have these outlines, the outlines of your pieces that will fit together, but it will also allow you to arrange them very nicely to make sure that when you cut them from your sheet material, you don't have a lot of waste. And I will simply go over the entire system here. So what we're doing is we're simply creating a mesh sphere. And this looks really wobbly, but it's just a mesh sphere with very few faces. And we're doing this by simply adding a mesh sphere and having our UV count really low. I can show you the mesh edges, so you can see how few edges we actually have in our geometry. Of course, you can have as many edges as you like, but you then will have to basically cut all of them and assemble them, and that can be a really difficult. So I would encourage you to start out with very few individual pieces, and you can always get more complex later on. We then triangulate this mesh. This is not always necessary, but I would usually advise you to do that, because a triangulated mesh always has flat faces. So a quad mesh can sometimes have quad faces that are not planar, that basically have some, not curvature, but they are not the edges, the vertices on the edges of the face might not be in one plane. So we then have a triangulated mesh, and we want to create two things. First of all, we want to get the boundaries of each of the faces. And we do this with the face boundaries component, and we will then offset these face boundaries just a little bit to the inside. And this is just for us to make sure that we have some clearance, and when we're then later fabricating these panels, we don't have them intersecting. Because if we didn't have this offset, these panels would be intersecting once you go into the real material that actually has some thickness to it. So we have these mesh surfaces, and we will also create circles on each of the midpoints between on the edges between two faces. So we get the mesh edges, we evaluate their length, and basically get the midpoint on each of these edges and create a perp frame there. Let me reduce the preview plane size so this is easier to see, like that. So now we just created a perp frame, and here we then draw a circle on each of these midpoints. Of course, this could be any geometry. This doesn't need to be a circle. This could be a square. This could be something more sophisticated. But for now, I want to use a circle simply to keep it as easy as possible in creating this. But of course, you can go as complex as you like here. And then we already add this to our region slits component. And this is similar to the simple example I showed before. We have our surfaces, we create one list from them, and then we have our region slits. And you can then go in and see that your regions are actually slotted in the way that they need to be. In order for us to then have a nicely flat laid out sheet with all of the different panels, we need to go through a few more steps. And one of these steps is to orient all of these panels that are basically oriented in space right now. We want them to be oriented on the base plane. So what we do is we simply get the midpoint of each of these panels as well as the circles, and we evaluate the surface. And we do this to get a plane that is perpendicular to all of these faces. And we can then use this with an orient component to orient all of these faces to the origin and the horizontal plane, the XY plane in Rhino and Grasshopper. And we can then use this as the input to our OpenNest components. I will not go into too much detail how the OpenNest plugin works, but we add the curves here and we create geometry from it. We might have to play around with the simplification, because sometimes the simplification can basically cut away or distort your geometry slightly. So you should figure out how much you want to simplify. We will also add sheets, and this is just our sheet stock. So the sheet of material that you have, whatever size it may be, you can set this here. You can also add the amount of sheets that you have. So if you have more sheets, you simply add more. And we also have some more options down here, which are options that influence the optimization process, and that also add different kinds of parameters. For example, if we want to have spacing between the different panels, or if we want to have the tolerance in the simplification, different kinds of algorithmic optimization stuff, how many iterations, how many populations the algorithm should create and evaluate. You can play around with these, but the standard parameters work really well. And then we have our OpenNest 2 component, and as long as the run nesting optimization is turned on, this will optimize and give you a good, well-optimized sheet. Of course, if you're doing anything else, if you're changing parameters in the front of the definition, you should always turn this to false. Simply to make sure that your definition stays responsive and fast, because every time OpenNest runs, it takes a second. So every time I do any kind of change here, the definition basically freezes until the nesting was done. That's it for the overview of this template. As always, you can go through this template and really check what each group and each component does. Most of it should be self-explanatory, but if you have any questions, you can also leave a comment. You can find the documentation page in the description, and there you can download the template as well as find more information about the OpenNest components that were used here.